match. Well, here's what it looks like once you add the anthropogenic forcing of aerosols and gases. So the difference between these two pictures is the main reason why scientists will argue that it is man-made, because they cannot explain the temperature changes without including CO2 and aerosol particles. So another test of a computer model is to look not at the global average temperature, but some other temperature. So global, here's the global ocean temperatures. The black line is the measurements. The blue band is what you get without man-made forcings. The red is what you get with man-made forcings. And then you can do that for individual continents. And in each case, you get a much better agreement with the observed record when you include the man-made gases and particles. So what I've shown so far is how do you build confidence in your computer model? Well, you test it against observations. And then you make predictions going forward. And that's what I'm showing here. So here's the gray band is the model results with all the forcings included. The black line is the measurements. And then going forward 100 years, you run your computer simulation to predict what's the temperature going to be. And there's two sources of difference. You've got different lines. I've got a red line, a green line, a blue line, a yellow line. Those are different futures of the global economy. So the yellow line is when everybody has stopped burning coal. And that limits the CO2 increase. And the red or the green is sort of a high growth, let's keep using the fuels we're using now kind of scenario. The second source of variability is when they rerun the model many times, they get slightly different predictions. And they use that to build up some idea of what the uncertainty of that future prediction is. So here's the average simulation under scenario B1, and then here's the range. So then you've got to say, well, let's look, how big is this number? So we've had 0.8 degree of warming so far, and we're predicting somewhere between an additional 1.5 degrees of warming up to an additional 3 degrees of warming. So what? Does that matter? So here's your observed warming so far. Somewhere between this level that we have now and some greater level of warming, there is a threshold where unacceptable consequences will happen. Right? We don't really know where that is. And for different consequences, there's different thresholds. If your consequence of concern is polar bears, there's a threshold for polar bears. If your consequence is flooding in New Orleans, there's a different threshold. Right? So this is a decision that the people, I'm getting political now, that the people and the Congress have to decide where's our threshold and then what can we do to stay below it. So what's worrying, what gets gloomy is that both our low emissions scenario and our high emissions scenario are above the threshold that a lot of scientists have proposed, which is we need to stop the future warming and we need to limit that to 1 degree above what we've already seen. So what are these consequences? One of them is sea level rise. So this is the observed sea level rise. So 20 centimeters, or what is that, 7 inches, is what the one estimate of the global mean sea level rise has been over the last 125 years. The models tell us that we can expect 1 to 3 times that amount in the next 100 years. And then another 50 centimeters in the next century. And then another 50 centimeters in the next 1,000 years. And if we get a rapid dynamical disintegration of Greenland or Antarctica, that would cause 1 in 7 meters of sea level rise. So these are the kind of numbers that let Al Gore show these pictures of New York City disappearing under this rising bathtub. Those are what you get if you get disintegrations of these ice sheets. And the edges of them are falling apart, but we're assured that for the next 100 years, the center won't also follow the edges. So here's what the IPCC panel says about the likelihood of different consequences. Increase in heat waves, have we seen them yet? Yes. Are we going to see increases in them? Very likely. Heavy rainfall, have we seen it yet? Yes. Are we going to see more of it? Very likely. Droughts, we've probably seen it already, and we're going to see more of it. Tropical storms, we've probably seen some of the increase, and we're likely to see more of it. Increasing coastal flooding, yes, we've probably seen it, and we're going to see more. The UN signed a treaty, a framework convention on climate change that said the UN's goal is to aim greenhouse gases at a level that will prevent dangerous anthropogenic interference in the climate system. Diplomats were careful not to try to define this because it's so difficult to define. But it's at least a goal to work for. I've talked about some of the big things: sea level change, extinctions of different species, unsustainable migration rates of other species as things try to move poleward or move to higher altitudes. We can turn up the AC, we can irrigate crops, but natural species don't have all these technological mechanisms to combat the change in the climate. So some of the signs that we're approaching these thresholds are these ice sheet disintegration events where scientists were surprised by the speed at which the Greenland and Antarctica ice sheets are falling apart. They were unpredicted. The Arctic ice also surprised scientists by the speed at which we seem to be approaching an ice-free Arctic Ocean. One of the folks out there arguing that we are either at or have already passed the dangerous interference threshold is this guy, James Hansen. And a couple of the things he has said is he is promoting this threshold of, well, we can't have more than a degree of additional warming. And since this was written, he's actually said, well, we probably have to back down on that some more. And that to avoid the dangerous interference, we have to stop CO2 from increasing above 450 parts per million. It's at 390 right now. It's going up 2 per year. So that gives us 30 years. So okay, so here's his proposed threshold. Here's where you have to keep CO2 to stay under that threshold. And he argues that based on very old climate data, that if we do not, we'll change the climate to a climate that the Earth has not observed for hundreds of thousands of years. So we will shift the climate into a region where it has been there, but it was a long, long time ago. And to us, that'll be a different planet. So if you agree with the things on the previous slide, then there are 3 facts. One is that future power plants must emit almost 0 CO2. Vehicles must eventually emit 0 CO2. And any coal that we use, the CO2 must be captured. If you agree with everything on the previous slide, there's no way of weaseling out of these 3 consequences. There are some opinions that gas and oil are very useful liquid fuels, and that we should use them as efficiently as possible. So that's one strategy of transitioning to a zero-carbon world, is to stop coal now, because we have those technologies, and keep using gasoline in cars because we're not as far along at figuring out how not to do that. You can argue that the United States must lead, and you can argue that vehicle mile per gallon standards should be increased, because that's a relatively easy thing to do. This is a map showing cumulative, like overall of history, emissions as the size of the countries. So people say, well, China is emitting more than us right now. But the CO2 stays in the atmosphere for thousands of years. So you've got to count all of it since we started industrializing. And there you see they're catching up, but they got a ways to go to surpass us. So a lot of the cumulative emissions are Europe, US, and the former Soviet Union. So I've already passed out links to my sources. You can email me. I'll send you 50 PDFs of all these things. And now I got my game. And 6 minutes to play it. So you're familiar with Millionaire. So that means I need a volunteer. And to answer questions, you can just answer them right out. You can have me take away 2 wrong answers. You have a lifeline to the audience, or you can ask the audience what the answer is. So first, I need a volunteer. Sir, come on up.
Oh, I get to come up?
Yeah.
Oh, Lord. Careful, I waddle.
What's your name?
Walter.
Thanks for playing, Walter. So unlike the real game, you can use as many of the options as many times as you want. So global land-ocean surface temperature between the year 1900 and now-ish, so 2007, how much did the global land-ocean average temperature increase?
C, final answer.
He was paying attention. Okay, over the last 125 years, how much has the global sea level changed by? A, no change. B, up 8 inches. C, down 4 inches. D, up 14 inches.
B, final answer.
See, I had to read him fast because I knew he was going to. Predicted sea level rise between now and 2100. Option A, between 1/2 foot and 2 feet. B, less than 6 inches. C, between 2 and 3 feet. And D, more than 3 feet.
A, final answer.
You ever think about graduate school?
Sign me up, fella.
I had to put a disclaimer in here that this model for predicting future sea level rise does not include the disintegration of either the Greenland or Antarctic ice sheets. Yeah?
Can I ask one question regarding?
Absolutely.
And so that sea level rise is from expansion and glacier?
This is from meltwater, but it's mostly from thermal expansion. So as you heat water, its density goes down a little bit. And that little bit, multiplied over the whole depth of the ocean, is enough to increase it. And it's not, and that's why it takes so long to fully play out, is that once the temperature signal starts working deeper and deeper into the ocean, the amount of water that needs to expand goes up.
So the Greenland and the Arctic ice sheet disintegrations, that would be like very rapid?
I don't know whether that's a decade or 100 years or 300 years.
It would take some time. Nonetheless, I would imagine if we had a fast meltdown of the Arctic ice cap, you have to remember that a great majority of the Arctic Sea that we cut through every year, you take away that much ice, you're going to see a 1/2 foot increase in the global sea level, just almost